el doctor Rossen Apostolov, quien participa también en nuestro evento de este gran evento de Bioinformática. Bueno, él va a exponernos su trabajo de Bioexcel Center of Excellence Extreme Scale Modeling and Simulator for Advanced Biomolecular Research. Él es director del Centro de la Excelencia Bioexcel para la Investigación Molecular Computacional y líder del Grupo de Investigación y Desarrollo del Software HPC en el KTH Royal Institute of Technology. Tiene un doctorado en Química Computacional de la Universidad de Osama, Japón, y un MB de la Universidad de Milano, Boccaccio, Italia. Es presidente del Consejo Europeo de HPC COE, tiene una gran experiencia e intereses en el desarrollo, crecimiento y sostenibilidad a largo plazo de infraestructuras de investigación, en particular HPC, así como en la prestación de servicios, el desarrollo de capacidades y el apoyo comunitario. Well. Okay. Okay, doctor. Well, Professor, you can start with your presentation. Has 40 minutes for your presentation development. Go ahead, doctor.
Thank you. Just a moment, please. Let's see now. Do you see my screen?
Yep. Yes, I can see.
Okay. Yeah. Hi, everyone. It's a pleasure to be here. It's really, I'm very excited to present at the Peruvian Bioinformatics Society. It's my first time to present and participate in a meeting with Peruvian scientists, so it's very interesting for me. I'm very excited to show you some of the work that we do. I hope there's a lot of useful information, knowledge for you there. So my name is Rossen Apostolov. Thank you, Diana, for presenting my CV in Spanish. I am based in Stockholm, in Sweden, in the Royal Institute of Technology, KTH. We have the Center for High Performance Computing, PDC, there, which is the largest at the moment in Sweden. For over 30 years now, we operate large infrastructures. And for the last almost 10 years now, I've been leading the Bioexcel Center of Excellence for Computational Biomolecular Research. The work that I will be presenting today is of what we've done in this center. So first of all, why do we need extreme scale computing for the life science research? There are many, many aspects. Some of them are, for example, that our bodies are made of tens of thousands of proteins, and we are now at a stage where we are able to simulate all of those proteins in atomistic detail, understand their function, dynamics, and be able to not understand how they work, but also control them. For example, for drug design, now a lot of large-scale computing sources are used for drug screening to filter out potential drug candidates. Development of methodologies is such as multi-scale modeling. So combining atomistic with coarse-grained models allow us now to simulate even a billion particle systems, such as whole cell models of viruses, for example. In the following slides, I will present several applications that we develop in the center. There's quite a few slides there. I'll be happy to share the slides later, just to give you a taste about the work that we do and how it might be interesting for you. So the first application I will look into is called GROMACS. It's for molecular dynamics simulations. It's one of the most popular codes around the world. And molecular dynamic simulations, some of you probably have used in your research, are a very versatile tool that can be applied for soft matter physics, or of biomolecular systems, or in materials science. And GROMACS has been developed for over 20 years now. It's a classical MD code with very large user base around the world. It's open source. It's freely available. It implements some of the some very advanced methods and algorithms that allow it to show really high performance and extreme scaling capabilities. There is a big focus on portability of GROMACS, so pretty much any hardware system that you can think of at the moment, all the major ones are supported by the code with various optimizations for each of these systems. In the group, we follow all the best practice for modern software development, which is really important thing to do. The code is quite large, and its performance and scalability are due to, on one hand, to the multi-level hierarchical parallelization in the code. So on one hand, when we run simulations on a single node on one of the machines, any machine, within the node, there's OpenMP that is used for threading, to launching all these threads on the node. There is a SIMD instructions instruction layer that is supporting again all of the major hardware architectures that are available on the market. GROMACS is running very efficiently on GPUs. I'll talk about this later, with support for CUDA, OpenCL, and SICO. For those of you who are working with GPU programming, these are the main backends at the moment. Also, internode, so internode parallelization in GROMACS is done with there's support for direct GPU communication, hierarchical ensemble parallelization, and we're working now on NVSHMEM. This is co-design work in progress. There is also multi-level load balancing. So while the simulation is running, it's possible to change the amount of work that is being given to different processors for optimal performance. So just quickly how parallelization schemes work in GROMACS. In a typical case of when you just run on a CPU, as at the top of this figure here, there are different stages in the molecular dynamics simulation method where we calculate different types of forces. And on the CPU, this calculation is done one after the other. Of course, we can parallel CPU, but we need to calculate each of these boxes sequentially, one after the other. If we have access to hybrid architecture, such we have CPUs and GPUs, then the traditional force offload parallelization works by moving part of the computation to the GPU, as on the left side you see in the green box here, the non-bounded interactions which take the most of the computational time. And then after calculation of the GPU, this is passed back to the CPU for integration at the end. Through the years, we were able to move even more of these calculations to the GPU, but still the integration step is done on the CPU, which is time consuming because the communication between CPU and GPU eventually becomes a bottleneck. So in the GPU resident parallelization schemes, there, as you can see, these black boxes where the integration is done, this stays on the GPU. So we do all the computation of forces where it's most suitable, but all the integration steps are done on the GPU, and it allows for very high scalability and performance. One big benefit of Gromox was work done maybe 10 years ago, where was done a lot of restructuring. New data structures were made in the code, allowing to create these clusters of 4 of each particle. So when one is doing the pair search for the non-bonded interaction, it considerably improves the search time, but also by doing this clustering of 4s allows to very quickly develop assembly kernels for different architectures, which are, of course, multiples of 4s. And this was another feature that helped with the big performance of Gromox. The work on the software is done in close collaboration with many of the big hardware vendors, NVIDIA, Intel, AMD, and others. One example of the usability and why it's important to have software that runs efficiently on both CPUs and GPUs is work that was done in Finland at CSC, the Center for Supercomputing there, which is one of they're part of Bioexcel as well. Loom is the fastest supercomputer in Europe, and it has almost 2.5 exaflop performance, sustained computing performance. It's a very large, very powerful machine, and this supercomputer has 2 partitions. One of them is only of CPU nodes, and the other one has CPU and GPU nodes. So at CSC, they did a very careful study of the performance of Gromox on using CPU only or GPU only nodes and see what we get in terms of performance. So what we can see here on the left is that using single nodes on the GPU partition, and the GPU partition has 8 GPUs and 64 core CPUs, as shown here on the right in this figure, while the CPU partition has effectively 128 CPU cores. And we can see that for any number of nodes with a reasonably large system of 1 million atoms, we get much better performance in the hybrid execution on the mixed GPU and CPU partition. What is also possible is that we can run multiple simulations, multiple trajectories simultaneously on a single GPU. So this GCD is GPU compute die. Of course, after some point we get saturation, and the performance will start dropping if we run more simulations. But it is possible to use these GPUs even more efficiently. As a summary of this study, we can show that for very large systems, so if you're running systems of millions of atoms, it is very beneficial to use multiple GPUs, so nodes with multiple GPUs. It is also possible to utilize efficiently GPUs for small systems. But the last point, which is not shown here in the previous graphs, is that if one is running very long and large simulations, in this case, can be shown that using GPU nodes, only a smaller number of GPU nodes, gives, with 2% of the big machine, you get the same performance as using 560 CPU-only nodes. And not to speak that in many cases, GPUs are much more energy efficient. There's a big team of Gromox developers. These are some previous contributors and current ones. The second application that I would like to present is how we are doing free energy calculations using GROMACS and another tool called PMX, which helps with the automation of the calculation of free energy calculations. I didn't follow the presentations before this one. What I heard in the last minutes from Fernando, there was a discussion about free energy calculations, but basically in the free energy calculation cycle is modifying molecules to. So there are different ways. One, you can alchemically change one ligand from one into another, from the blue to the red one, and in this way, computing these delta G's for these transformations, you can see what is the actual free energy of the transition that one is interested in or certain structure. So with the PMX, it's possible to run amino acid mutations, nucleotide mutations as well, and also ligand binding. It's possible to calculate relative free energies or absolute protein ligand binding free energies, which is something very important for pharmaceutical research and for drug screening. So using PMX, it's much easier to automate the process of drug screening. And we've done in Bioexcel this large scale drug screening running on 500 nodes at the time, and screening through many protein ligand systems, calculating almost 500 different relative binding free energies with excellent correlation using different force fields. Now, this is done on HPC infrastructure, but it's also possible to run it on cloud infrastructure. And in fact, there are many companies that are using, for example, Amazon Cloud Services instead of hosting their own supercomputers. And we can show that it is also possible and very fast and efficient. It's even very cost efficient to use cloud infrastructure to run such screenings. And as you can see from these plots, with PMX, one is able to get extremely good estimates for the energies on par, and in some cases even better than other commercial software. PMX is also open source and free. And PMX is developed by the team of Bert de Groot in Max Planck Institute in Germany. Now, another application that we're developing is the Bioexcel building blocks. And Stanislao, when we exchanged emails about this meeting today, said he was very interested in having a workshop on BioBB. So we need to see when it will be possible to arrange for that. Actually, I'm skipping a bit ahead, but later we can discuss in future. Maybe we can do some remote presentations and training that focus more in depth on each of the applications. So about the Bioexcel building blocks, as I'm sure you have experienced, any scientific case that one is working on computationally typically involves many different steps and tools and bigger applications. So I was talking about GROMACS and PMX. Usually, before you do the big production run, one needs to get data from a database. You need to maybe convert it in a suitable format. Maybe you want to do some pre-processing before you feed it into the simulation engine. After you get the results, you need to analyze those, do some statistics, you might want to feed them back into the engine and so forth. So typically, there will be many application steps involved, which ultimately hurts the productivity of researchers. And if you have access to a large supercomputer, it's not very convenient sometimes to, you gain so much of having access to a fast machine, yet you need to do a lot of manual work. Not only there are many steps involved in a typical application, but in some cases you have many different tools that do similar type of calculations. And nowadays for biomolecular modeling and simulations, there are many different ones that are routinely used by the communities, and I'm sure some of you have been using some of these applications. To help with this problem and to help with the productivity of researchers, Bioexcel, we developed these so-called building blocks, where each of these building blocks is kind of wrapping a single tool that does only one, whatever its main purpose is, something in the spirit of, let's say, the Unix tools. Now, if one provides this library of building blocks with the necessary input and output connections, with this framework, it is possible to build these complicated workflows that express your own problem within a single workflow. And this dramatically diminishes the amount of manual work that one needs to do. So BioBB has been developed for many years now. Currently, there are now we have more than 17. This is the last stable release. We just released a new one this year, but I haven't updated the slide. There are many modules that support many of the popular tools that you might need, like for molecular dynamics, quantum mechanics, also machine learning, virtual screening, and so forth. The way what is needed to run those workflows, first one needs to build this workflow using BioBB to construct the workflow. Then this workflow is given to a workflow manager. We've been often using PyComps, which is developed by the Barcelona Supercomputing Center, that it distributes and manages its execution on the server. We've done some large-scale scalability on one of the European supercomputers. It's not that big yet. It's a mid-range system, Discoverer. And then we see that we can get, with a strong scaling case, up to like 250, about 300 nodes, a pretty good scalability. Of course, then you get saturation and it hurts the performance. For weak scaling, similarly, it's very good scaling up to about 250, 300 nodes. Another thing that we investigated was the malleability of the execution, where one is able to efficiently use the available CPUs, those that are idling and those that are active, to minimize the amount of power that is being consumed. So fine-tuning the workflows and the workflow manager, we are able to run at scale, but very efficiently and in an energy efficient manner. If you're interested in BioBB, you can visit the website, and there's a lot of demonstration workflows there that those are examples that you can try out, and there are templates that you can build also your own modules. Maybe if we arrange a workshop in the coming months, Adam Hospital, the main developer of the tool, is can show you in more details how this is working. All of this work is done by Bioexcel, which the center, we have several other applications that are being developed, but it provides a comprehensive set of tools and support structures, which I will mention in a while. But very briefly, take-home messages from these tools until now is that supercomputers are now being deployed across the world. They offer tremendous power, and they can drastically speed up your research. It's very important to learn how to use them efficiently. And we see more and more adoption of automation frameworks, such as workflows, that take away the manual work and do the computing, and so we can focus on the more fun, creative part of thinking. At the same time, HPC technology is developing very quickly, so we need to stay at the forefront of the technology development as well. At the end, I want to say a few words about the community impact, because this is something very, very important, especially nowadays. Whenever we have any grand challenges that we need to tackle, such as like the COVID pandemic, it was a very, very good example, and used by informaticians are very well aware of the challenges scientifically that were there. Now, as mentioned, we have the compute infrastructure across the world. Europe, the States, China, Japan. Europe has collaborations also with Latin America. There was a long-running project there on HPC as well. So we have the infrastructure. We need the tools and the data, and I just spoke about some of those applications. The next part there is the expertise, because even with those advanced tools and the infrastructure, the researchers really need to be able to efficiently use the applications. It's not very trivial to make the best out of these fast machines. The applications are powerful, but they're also, they have their particularities, and so increasing the expertise is really vital for the development of science and support of researchers. And there comes the final block, which is the community building, and that's where these centers of excellence came into play. In 2015, the European Union realized the need for this community, this more holistic approach in the support, and established a number of centers. One of them is Bioexcel, but there are several others in different domains, also for material science, energy research, weather forecasting, engineering sciences, and so forth. And in Bioexcel, we have three main goals. First one is to provide life science researchers with this high quality and user-friendly software. It's a never-ending work, because we, as I said, technology is rapidly developing. We always need to keep up with the trends. Making software user-friendly is very it takes a lot of effort, and many funders are not willing to provide support for that. And doing it commercially is also not very easy. So the first objective is to develop the software. The second one is to increase the expertise and the skills of researchers, which we are doing through a very extensive training program, where we look at the skill gaps of researchers. We look at what is available as training material, what is missing, and for all the new features, methods that are being developed in applications, we try to very quickly produce tutorials, run a lot of hands-on sessions, workshops, and so forth. And the final one is to strengthen the community, because nobody can be very successful in solving large problems on their own, and there's a lot we can gain from working together. Bioexcel develops a number of services in addition to the applications and the tools that are provided as open source and free applications. We have support forums at ask.bioexcel.eu, where all of these tools have dedicated categories. We have specific documentation website, docs.bioexcel.eu, where you can find a lot of links to tutorials, manuals, best practice guides, and other useful material. We've been also running since the very beginning webinar series on our YouTube channel. You can find, I think there's like more than 70 now of them, with thousands of views. And as I mentioned, we have this extensive training program. From last year, actually, we started the Bioexcel Ambassador program, where we have representatives in different countries. Currently, this is only in Europe, but we have some plans to expand it outside of the continent. Unfortunately, our funders at the moment, like in the first two phases of Bioexcel, it was much more relaxed with the regulations, but now we can run events only in Europe because of how the funding scheme is structured. Meaning we can't physically, on Bioexcel funding, go to Peru, for example, or needs to be in Europe. But we are exploring how we can expand the outreach through different funding schemes. For example, we have very close collaborations and different working programs with Japan, with India. We're starting one most likely next year. So hopefully with Latin America we can also do more. I encourage you, if any of the topics are relevant to your work, you can subscribe to our newsletter. It comes out every couple of months with useful links and pointers to upcoming events and webinars. Our Twitter channel is reasonably active with interesting posts. As I said, the YouTube channel is, I think, will be very useful for you. So I'll stick to this 30 minutes presentation and have some time for questions. Thank you very much. You're welcome to subscribe to the newsletter, visit our website, and also feel free to drop me an email to rossen@kth.se. I'll be happy to be in touch and see how we can help each other. So yeah, thank you very much, and ready to take any questions you have.
Okay, thank you so very much, Doctor, for your presentation. I think we have some questions in the chat for you. Let me check this. Okay. Oh dear, Estina's now. Yes, go ahead.
Thank you very much. Thank you very much, Dr. Apostolov, for your lecture. It was really, really enlightening. We appreciate your time here. I would like to ask about further collaborations with Bioexcel. How a researcher, young researcher, or senior researcher can make in contact with your group and make some collaboration in order to share computational resources, techniques, etc.
So as I said, we need, so there are different ways. We can arrange for some online training, depending on the interests and what's the capacity at the moment. For access to compute resources, it's a little more difficult than they're provided usually to European researchers or to collaborators of European researchers. So if we have a joint project where, say, your group is working with us on a given project, then you as collaborators, you can be part of the allocation that is available to the European researchers. When I mentioned Japan, India, and some other countries, now we have with Korea and others, there are quite often there are grants and calls for proposals for joint work between different countries or even whole continents. Like there used to be Europe, Latin America collaboration activity on HPC that was providing funding for such type of collaborative work. As always, it comes down to funding and resources. So if you are aware of any funding scheme that we can jointly apply for, I'll be happy to explore the possibilities for that. Otherwise, some of the online trainings are those that are online and more like demonstrators. Then we have, it's not like unlimited number of attendees, but pretty much like hundreds of people can join and attend. The physical meetings are more difficult. I'm talking specifically for Bioexcel specific funding, because Bioexcel is a consortium of different universities. And in some cases, universities have other funding, which is not as restrictive as the main European one.
And I have a second one that I found sorry, that I found quite interesting. How Bioexcel is engaged or work together with the industry. Can you give us some example or some experience about that? Because I think in this event we wanna show that academia and industry can work together. So can you please explain a bit more? Thank you very much.
Yes, I should have put a few slides about it as well. Yes, we work a lot also with industry, specifically with pharma companies. Many of the companies are using our tools, Janssen, AstraZeneca, for example, and many other small biotechs. Gromox is quite popular for those that run MD simulations. They incorporate it in their workflows. Small biotechs, several of them are also adopting BioBB to develop their own workflows. PMX is very popular also by pharma companies for drug screening. There's another application which I didn't present here. It's very popular for integrative modeling and docking. It's called HADOC. Maybe you've heard of it. HADOC is also used by dozens of pharma companies. Also, companies working on genomics for agriculture. for example, for selecting seeds with desired properties. So they look at the genes of different seeds and selecting for resistance to drought or to bugs and so forth. So Haddock is being used by such companies as well. So with industry we have close contacts. With industry is it's a little more specific because they usually want results very quickly. They want close engagement. Often work is done under NDAs, so it takes a bit more time to negotiate the terms of collaborations. But yeah, we have extensive collaborations with industry as well.
Thank you very much, Doctor.
Okay. Another questions, maybe? Oh, well, Karim, yes, you're out.
Thank you, Dr. Rossen Apostolov. My question is if any researchers need a particular software to install, how is that procedure? It is quite open to install any different softwares.
Yes, so all the applications are open source, so you can download them for free and you can install them on your machines. There are installation instructions. There are also manuals and tutorials about using them, especially like for introductory beginner tutorials. There are many of those on docs.bioexcel.eu. Yes. So here, docs.bioexcel.eu, there are links to that. Also, the website, if you go through, I think they're on the, where each of the application is explained, there are links to material. So the applications are free for you to install on your machines. Many, at least in Europe, we are trying to provide them on all the big supercomputers. Some, specifically GROMACS, must be available on most of the large supercomputing machines in the world because it's quite popular. And if you have any problems with the installation or the setup, the forums at ask.bioexcel.eu. For GROMACS is gromacs.bioexcel.eu, but you'll find it there. It's are very useful, and you will get your questions answered quite quickly, I think. Yeah, and if you have anything else, I'll be happy to help with any other information that you need.
Thank you. I'm impressed of how much tutorials links are on YouTube, so we have a lot of materials to check. Thank you.
I would say try them out, see how it works. If something's not working, drop us a mail or a question at the forums. And,
yes, thank you, Doctor.
Okay, thank you again, Professor. We hope you will join us at our next events. Thank you.
Thank you very much, and congratulations again on the anniversary. Yeah, let's keep in touch and explore options for collaboration in the future.
Oh, thank you, Professor.